I'm going to take this time to just do a little playing to show you how, in fact, sometimes when you come upon intuition or come on something you solve algebraically, you want to check it in an engine you trust. And so we're going to check that at this point. We're going to check this concept that the swipe distance, or the distance to offset through the origin, is equal to the slope-intercept of the line times the cosine of the angle which describes the line in the plane. So I'm going to do that first by getting really good at drafting and remembering, going back to my rules of turning off all my clickers along here, going here, drafting a line now from 0, 0, 0 at 100 at an angle of 0, zoom extents, and then learning to then left click on something. And even going back to this, left click on something or saying minus array, select my objects, polar, center point, shift right click, the end point of that. Number of items 4 and 360 degrees. Great way. And rotate the objects, zoom extents. Now you've got something where you've got your coordinates. And I'm just going to go ahead and draft off now, for instance, as we're doing this, I'll do some of these first in a positive direction. I'm going to make sure that we put that now. Learning to right click, change the properties of something, all kinds of different ways to do that, of course. But I'm going to put that on a layer called object at this point in time, which is frozen, as I've never set my home machine up correctly, even to this day. We're going to go ahead and make that to be my current layer, and then close this up. So what was our supposition as I get rid of that? Our supposition was that if in fact I wanted to offset this line, this vector, if I drafted through the origin, that the offset distance, which would basically then give me this swipe distance here, if I go ahead and do this, hang on, I'm going to look at the phone. I apologize for that interruption. What we're going to remember is that this swipe distance should be equal to the slope-intercept times the cosine of this angle or this direction. And we, of course, could get the cosine by knowing that the tangent of the angle is equal to the angle, etc. Tangent of the angle is equal to the slope, but in this case, it's going to be a little easier just to list it, isn't it? So let's go ahead and find out by using an x-line, and I'm going to specify a point at the end point of here, and another one. Go back again, try it again, x-line, shift right click the end point of here, shift right click the end point of there, and remembering how important it is sometimes to then change the layer and the draw order on things. I'm going to go ahead and see if I can put that into something that's behind the other thing, and I can do that, of course, by right clicking and changing the draw order, sending to back. Not so good, but I can now do ID the intersection of that. So that intersection is 13.8265. And what we are guessing, 0.8265. We're guessing that when we do this, O for offset, T for through, this object through the shift right click, the intersection of that, and look at that distance from near, N-E-A-R, of here, to perpendicular to that. We're going to guess that 9.3743 is equal, in fact, to that slope-intercept distance of 13.82 times the cosine of the angle we get when we list this here. If we list that there, we have an angle of 47.33. And so we're going to realize when I look at the cosine of 47.33, I'm going to guess that the cosine is going to be, this is not going to prove to be true. So let's check it out. So we had this 13 And we're going to go ahead and take out the calculator now. Start, right? We're going to take that 13.82, file, new, run, file. We're going to run that calculator. And we're going to make sure, of course, that our mode is set correctly. And we're going to take 13.82 times the cosine of 47.33, and we get that 9.36, which is in fact what we had. Now, my intuition, even as I'm doing this, isn't necessarily correct all the time, but realizing that one can go about doing things that way is pretty useful in terms of combinations of skills. So what we realize then is that this swipe distance, which really gets us then, in fact, what is the area. I'm going to go line here from the shift, right click the endpoint of that to the right click endpoint of that. Offset T through. We have to realize the reason we want the swipe distance is so that we can then essentially shift this vector here and then move it down here and replace it with, in fact, we can replace this single vector. Let me get rid of this. We can replace this single vector here with this vector, and then a bit of a torque. I'll just use the arc here. Right? A torque that's going that way, which in fact would be a vector. I'm going to now go v point 1, comma 1, comma 1, which would be a vector actually, if you think about it, down into the board. It would be negative, so it would be something like a line from 0, comma 0, comma 0 at 0, comma 0, comma minus the area. So let's just make it minus 30. V point 1, comma 1, comma 1. And as you're used to, V point maybe 0.25, comma 1, comma 1. 0.25, comma 1, comma 1. And then that concept that you would have this vector here be replaced by this vector and that torque. So, in summary, to get the offset distance or the swipe distance for a point force applied anywhere on a plane, you take the slope intercept of the line of force and you multiply it by the cosine of the line of force, and that will get you effectively the swipe distance. Thanks for listening.